everyone, my name is Jasmine Brown and I'm presenting my Physics 2211 Lab 1 report on constant velocity. So the purpose of this lab is to apply Newton's second law of motion, also known as the momentum principle, to a real-world scenario. And so this lab makes use of a tracker app to graph a position versus time graph of the object's real-time movement. And then we will compare this to a computational model, also in a position versus time graph of Newton's second law made from a glow strip code. So, just to explain, Newton's second law describes the change in momentum of an object over time due to the surrounding forces acting on the system. So, if there is no net force acting on a system, then there will be no change in momentum, so the velocity will remain constant. And we can see this in our momentum update formula, where the final momentum is equal to the initial momentum plus the net force times delta t. But if there is no net force acting on this, then we have the final momentum equal to the initial momentum, so there's no change in momentum. And this can further be seen in our velocity update formula, where we divide each term by mass, and then we're able to get that our final velocity is equal to our initial velocity plus our F net times our delta t divided by mass. But once again, if there is zero net force, our initial velocity is equal to our final velocity. And then we have what's known as a constant velocity. Here we are in the tracker app, and for this portion of the lab, I set up a golf ball and a flat tabletop surface. And in this case, the golf ball is the system and the table is the surrounding. So I started the tracking app at this time point, and I recorded it from where it began to roll after an external force, and I ended the tracking where the object began to leave frame. So if we play this, we can see it going, and then stopping when it leaves the frame. And so we can see that the recording was about 1.9 seconds, and we started off with an initial position indicated here, which is about 0. And indicated by this point here, we can see that the initial velocity was about 0.424. And this indicates the x component of the velocity, since the object is only moving in the horizontal plane. So in order to model this experiment computationally, we need to set up the same conditions that are present in the real-world experiment. So for this, I needed to change provided Python code in GlowScript, and so I have the position vector at 0, 0, 0 in all components, and I changed the x component of the vector to match the x component of the velocity present in the real-world example. And then I also changed my delta t to match the one present in the real-world example, and I found this by seeing the change in each time step that was recorded for the frame rate. And so for our code of the computational model, this code depicts Newton's second law along with the position and velocity update formulas. So in this line, we can see the position update formula being used, where we have that final position being the initial position plus the velocity times delta t, and this initial position continues to be updated by the previous final position. This is the same for the velocity update formula, where we see this new velocity being updated by each time we go through this while loop. So here we have a graph that shows the tracker app data versus the computational model. So initially both follow the same trend line, but as time increases, we can see the slope of the experimental tracker data decreases, which indicates that there is a decrease in the velocity as time continues. And so while the expected data from the computational model follows a constant velocity, as seen in Newton's second law. And so this is due to the fact that there are outside forces acting on the ball, such as friction, which acts in the opposite direction to the object's travel, which therefore slows the velocity. So some possible sources of error present in this experiment could be human error, such as the tilting of the tabletop, which may cause the ball to not move in a perfectly straight line. To answer our essential questions, I initially made it so that my ball went in the positive x direction. So switching the positive x and negative x would mean that my ball would be going in the negative x direction, and so this would only change the direction of the velocity, but the speed would remain the same, where the ball would continue to slow down, but in the negative direction. And so we cannot say that the net force is 0, because in order for the net force to be 0, we would have to have a constant velocity, but since we didn't have a constant velocity, there were unbalanced forces acting on the object as it was moving. And so we also cannot say how many forces were added together in order to have a net force of 0, and this is due to the fact that there could be various forces that we're unaware of that are contributing to balancing these forces, such as a force that is equal and opposite to friction or air resistance. Therefore, if the net force is 0, the object will remain a constant velocity, but if it is not 0, the object will have a change in velocity.